Welcome viewers to the third segment of the sixth lecture for the online series of lectures for the course of differential geometry. Let me begin this segment with the notion of curves in a manifold. A smooth curve in a manifold M is a smooth map denoted by C from the open interval a comma b to M. Usually, we assume that the origin of the real line 0 is contained in the open interval a comma b and say that C is a curve starting at the point P in M if C of 0 is equal to that point P. The velocity vector which we denote by C prime at t0, this velocity vector of the curve C at time t0 in the open interval a comma b is defined to be C prime at t0 is defined as the differential C star at t0 acting on the tangent vector d dt at t0. And this is in the tangent space to M at the point C of t0. I want you to remember that C, the differential C star at the point t0 is a linear map between two tangent spaces. The first one being the tangent space to R at the point t0 and the target tangent space being the tangent space to M at the point C of t0. Okay, so that's the definition of the velocity vector of a curve at a given time. Now I want to remark about the possible notational confusion. It's the case when the target manifold for this smooth curve is going to be the real line. So we are considering the special case when we are focusing on the smooth map from the open interval a comma b to R. Okay, and by the notation that we have already introduced while defining the velocity vector to a curve, C prime of t denotes uh, a tangent vector lying in this tangent space, right? And hence this guy is a scalar multiple of this basis vector in this vector space, right? Hence this object here is a vector. It's a scalar multiple of this tangent vector, and hence is a vector from the definition of the velocity vector to a curve at a given point or a given time. Now, in ordinary calculus, this is a real valued function. The derivative of a real valued function is which is denoted also by this notation in calculus, and it's customary to denote this guy as c prime of t in calculus, in the calculus of one variable. Single variable calculus, we do that. So we don't want to be confused with this. We don't want ourselves to be confused with the usual derivative in single variable calculus with this velocity vector to a curve at a given time. So in order to resolve this confusion, we are going to denote the scalar, which is the ordinary derivative in single variable calculus, by c dot of t. Okay. So this is a scalar valued function or a real valued function, and c dot of t is going to be a scalar, which is the ordinary derivative of this real valued function with respect to time. That's what we are going to denote by c dot of t. And we are going to reserve c prime of t for the velocity vector to a curve at a given time. So in this case, c prime of t is a tangent vector, and hence is a scalar multiple of this basis vector del x del over del x at c of t. Okay, good. Now let me give you an example of this notion of velocity vector to a curve at a given time, which we call example 2. Define this map C from R to R squared by C of t is equal to t squared comma t cubed. The x component of this curve is t squared, the y component being t cubed. So we can draw the graph of this map in the following way. This is the x component, this is the y component. Okay, this is +1 and this is -1. This is +1 along the x-axis, and in the negative x direction we have -1 here, somewhere here, and the curve somewhat looks like this. Something like this, and it has a nice name called cuspidal cubic. That's the caption of the figure. And according to the definition of a velocity vector to a curve at a given time, C prime at t0 is going to be the differential of this curve at t0 acting on the tangent vector d dt at t0, okay, and this object is in the tangent space to R2 at the point C of t0. Okay, so this is a vector space of dimension 2, and hence C prime at t0, C star comma t0 acting on this tangent vector is going to be a linear combination of the basis vectors in this tangent space. So let me denote the coefficients of this linear combination with A and B. So this is equal to A times del by del x at C of t0 plus B times del by del y at C of t0. Here A and B are real numbers. Okay, let me denote this equation by 18. So evaluate both sides of 18 on the function x, and that will give us this this coefficient a. So on the right side, this coefficient will survive only. We'll have a on the right side, and on the left side we'll have c star comma t0 acting on d dt at t0 acting on the function x, and that is equal to d dt at t0 x composed with c, using um, the the definition of differential. So what is the x component of the curve? That's t squared. So this is equal to t square, the derivative of t square evaluated at t0, which is 2t0. This is equation number 19. And we do the same trick on the function y. Evaluate both sides of 18 on y to yield b is equal to c star comma t0 acting on d dt t0 acting on y, right, which is d dt t0 acting on y composed with c. What is the y component of this curve? T cube, and that gives us 3t0 squared, right? This is equation number 20. Good. Now, using 18, we can plug in these two values in 18 to find c star comma t0 acting on d dt at t0, which is nothing but we know that this is c prime of t0. C prime at t0 is equal to 2t0 del by del x at c of t0 plus 3t0 squared del by del y at c of t0. Okay, this is equation number 21. So what does 21 tell us? let me write it for you. 21 tells us that in terms of the basis del by del x at c of t0 and del by del y at c of t0. In terms of this basis of the tangent space to R2 at the point c of t0, C prime at T0 is represented by this column matrix 2T0, 3T0 square. Okay, so this second example inspires us to write down the following proposition. So let me state the proposition, the proof of which will be left as an exercise. Proposition 5. Velocity of a curve in local coordinates a very useful theorem. Let C from the open interval a comma b to m be a smooth curve and let u comma x1 x2 all the way up to xn be a coordinate chart about C of t. Okay, so C of t is a curve in the manifold M, something like this. This is the manifold, okay, and this is C of t, which is a map from this open interval a comma b in the real line to the manifold M, and I want a chart that contains this curve, something like this. This is the open set U containing C of t. Okay, now write the n components of this curve C of t in the following way. Ci is equal to xi composed with c. So what are these function ci's? Each ci is a function from a comma b to r, right? Xi's are the local coordinates for this chart. So this Ci is the ith component of the curve C in the chart. Okay, then C prime of t is given by C prime of t, which is an element in the tangent space Tm c of t, right? And this is equal to, according to this proposition, um, the sum over all i's, where I runs from 1 to n, and there is, so the the basis vectors in this tangent space are del xi at c of t. So it's the basis expansion of this tangent vector in this tangent space, and the coefficients of this linear combination are c dot I of t, okay, where each ci is a real valued function, okay. So this c dot I, ci dot is the usual calculus derivative, okay. So when I mentioned this notational confusion thing a while ago, I mentioned that I'm going to reserve this c dot thing for the calculus derivative. So this is the calculus derivative here. Okay, so thus relative to this basis, to the basis del by del xi at c of t, I runs from 1 to n. This is the basis for the tangent space t tm, the tangent space to m at c of t. Okay. Relative to this basis of this tangent space, the velocity c prime of t is represented by the column vector c1 dot t, c2 dot t, all the way down to cn dot of t. Okay. So remember that in the previous example, in example 2, we had only two components of this column vector, because there we were dealing with the two-dimensional Euclidean space R squared. That was the target manifold. I mean, the manifold in which we were having this smooth curve. But in this case, n can be anything, and hence we have an n component column vector in general. So like I said before, ci dot of t, which is the ordinary calculus derivative, this is a scalar, okay, is the derivative of the real valued function ci of t. Okay, so I skip the proof. I leave the proof as an exercise for the audience. Now, another important proposition, which I call proposition 6, is about the existence of a curve with a given initial vector. Existence of a curve with a given initial vector. So I'm not going to provide the proof. Let me state it to you for any point P in the manifold M and any tangent vector x sub P in TPM. Okay, so we need to fix a point and fix a tangent vector in the tangent space Tp of M. So we need to fix a point P on the manifold and fix a tangent vector x sub P in the tangent space TPM. Given this data, there are epsilon positive and a smooth curve C from the open interval minus epsilon to plus epsilon to the manifold M such that C of 0 is equal to P and C prime at 0 is going to be equal to x sub P. Okay, we can always be able to find such a curve such that the curve starts at the point P and the tangent the velocity vector of that curve to the curve at the point 0 is the given tangent vector x sub P. Okay, it guarantees, this proposition guarantees the existence of such a curve. So the proof is omitted. Now, proposition 7. Suppose x sub P is a tangent vector at a point P in a manifold M, and F is a germ of smooth functions on the manifold M at a point P. Okay, if C from this open interval minus epsilon to plus epsilon to the manifold M is a smooth curve, if this guy is a smooth curve, starting at P with the velocity vector at the initial point, at the initial time, to be equal to x sub P. We know that such a curve exists by proposition 6. Then x sub P acting on F, this is supposed to be a number because x sub P is a point derivation and F is a germ of smooth functions, and then x sub P acting on F. F is an element from the germ of smooth function, from one of the germs of smooth functions here. This is a set of equivalence classes of smooth functions at P, right? In fact, it's an R algebra. We have seen it in the first segment. So x sub P acting on F is a number, and this number is equal to this d dt at 0 acting on f composed with c. It means that we have to derive f composed with c with respect to t and take its value at the point t equal to 0, and that number is nothing but x sub p acting on f. Now here is the proof. Proof is very simple. X sub p acting on f is equal to c prime of 0 acting on f, since c prime of 0 is x sub p, and we know from the definition of velocity vector to a curve at a given time that this is nothing but c star 0 acting on the tangent vector d dt 0, and that acts on f. And now from the definition of differential, we know that this is nothing but d dt at 0 f composed with c, right? QED. Good. Now, computing differential using curve. A very important result that we'll use in a short while in a very interesting example um, for the smooth map of left multiplication in the context of matrix Lie groups. Okay, so let me state a result by means of proposition 8. Let f from n to m be a smooth map of manifolds P is in n, P is a point in n, and x sub p is a tangent vector in the tangent space TPN. If C is a smooth curve, starting at P in N and with velocity x sub p at P. We know that such a curve exists by means of proposition 6, right? Then the differential of this smooth map f at the point P acting on this tangent vector x sub p is equal to the velocity vector of this smooth curve f composed with c at the initial point 0, at the initial time t equal to 0. Or this is also the same as f composed with c star comma 0 acting on d dt 0. Okay, this is what we need to prove. In other words, f star comma p acting on x sub p is the velocity vector of the curve F composed with C at F composed with C evaluated at 0, that is f of p. C of 0 is p. Okay, so this curve is in the manifold M. Proof. By hypothesis, C of 0 is equal to P, right? The curve C starts at the point P, and it has the initial velocity to be x sub P, so that C prime 0 is x sub P. Now, F star comma P acting on x sub P, that's the left hand side, is equal to F star comma P. What is x sub P? Is C prime of 0. And now I invoke the definition of velocity vector in terms of differential. This is equal to C star 0 acting on the tangent vector d dt 0, right? So now this is the composition of these two maps, which is F star comma C of 0, P is C of 0, composed with C star comma 0, right? And this composition of these two maps act on this tangent vector d dt 0. Okay, and this is equal to, so by chain rule, this is going to be F composed with C, star comma 0 acting on d dt 0. And this is nothing but the velocity vector of the composed map, or the composed curve F composed with C at the initial time 0. So this is the velocity vector to the curve F composed with C in the manifold M at F of C of 0 is equal to F of P in M. Okay, QED. Good. Now, and an example using this proposition 8 and a couple of the previous propositions. Example 3. Differential of left multiplication. Okay, so the fundamental object that we'll be working on is called the general linear group of dimension n. Okay, it is a group from the algebraic point of view, meaning that it obeys all the structures or all the properties needed to have the structure of a group that we study in elementary group theory. It is called the group of all invertible n times n real matrices. It has a name. It's called the general linear group. The general linear group. Okay. Now we'll look at the map L. So we first of all we fix an n times an invertible real matrix G. Fix G in GLN comma R. Okay. Then define a smooth map from GLN comma R to itself. By the way, GLN comma R is an open subset of R to the n square that we have seen earlier while we were giving definitions of, uh, of, of a smooth manifold. We have seen that GLN comma R is an open set of this Euclidean space R to the n square, and hence GLN R is a manifold of dimension n squared. So LG is a smooth map from the n square dimensional manifold GLNR to itself. So how do we define this map? This is called the map of left multiplication, because LG acting on an element B in GLNR is equal to G times B. It's given by the left multiplication by the invertible matrix G. This is true for all B in GLNR. Okay. So what are the data? We are given this smooth map from the manifold GLNR to itself, and now we need the invertible n times n identity matrix over reals identity matrix, and is denoted by I. So I is in GLN comma R. Okay. And now we take the differential of this smooth map at this point identity of the manifold GLNR. So this is supposed to be a map from the tangent space Ti of GLNR to T sub LG acting on I, which is just G times I, which is G, TG of GLN comma R. Okay. Now pick up. Okay. But before that, I need to mention the problem. What do we need to show? So this is a linear map, okay, between two tangent spaces, and we need to show that this linear map is also left multiplication by G. Okay, what do I mean by left multiplication by G will be clear in due course. Okay, so let me get started with the solution. I need to fix an element in this tangent space. X belongs to this tangent space, at the identity of the manifold GLN comma R. Okay. And we know that I is a point in GLN comma R. Okay, good. So by proposition 6, one can find a curve, one can find a curve C of t in GLN comma R. Okay, what is this map C? It's a map from A comma B to GLN comma R. So it's a curve in the manifold GLN comma R such that C of 0 is that particular point identity matrix in GLN comma R, and C prime of 0 is that tangent vector in this tangent space. It's guaranteed by proposition 6 that we can find such a curve. Okay, so let me erase these things. Now, by proposition 5, there is a chart U comma Rij. Here I runs from 1 to n and j runs from 1 to n. Okay, so how many coordinate functions are there? N square coordinate functions, right? Suppose r11, r12 all the way up to r1n, then r21, r22 all the way up to r2n, finally from rn1, rn2 all the way up to rnn. So there are n square such coordinate functions. So there is a chart U comma Rij about the point C of 0 in I in GLNR such that you can write the velocity vector at the initial point in terms of the basis vectors in local, the basis vectors in the respective tangent space. C prime 0 is equal to sum over all ij's C dot ij at 0 and del by del Rij at I, right? This can be done by means of proposition 5. Okay. Now we define a map psi from this tangent space Ti of GLN comma R to the vector space of all n times n real matrices, all the matrices invertible, non-invertible, everything. The zero matrix, everything is there. Okay. So psi of, so remember C prime of 0. C prime of 0 is what? C prime of 0 is, this is X, right? This guy is in this tangent space. So psi of C prime of 0 is equal to psi of this guy, right? By this equation, psi of sum over all ij's, C dot ij of 0 del by del rij at I. And we define this, the map psi, to produce this matrix C dot ij at 0, where ij runs from 1 to all the way up to n. Okay, so this is C dot I. So this is how I define this map psi from this tangent space to the to the space of all n times n real matrices. Good. Now, now about this left multiplication map LG, which is a map from GLN comma R to itself, right? I have defined this map before. Now, how about LG acting on this curve C of t in GLNR? That is going to, so this is nothing but the composition of these two maps. LG composed with C acting evaluated at t. Okay, so this is nothing but G times C of t. This multiplication is matrix multiplication of two invertible uh, n times n real matrices. Okay, now, so this is a smooth map between from the smooth manifold G and LR and R2 itself. So by proposition 8, the differential of this map at the identity matrix is an element here. This guy acting on X, where we have seen that X is equal to C prime of 0, and this is an element in Ti GLN of R, right? So by proposition 8, this thing is nothing but LG composed, L sub G composed with C star comma 0 acting on DDT at 0. Okay. This follows from, or if I want to write it this way, LG composed with C prime at 0. So LG composed with C is a new curve in GLNR. So let me denote this new curve by C tilde of t to be equal to LG composed with C at t. So what is the starting point of this curve? C tilde of 0 is equal to LG composed with C at 0 is equal to LG, L sub G acting on C of 0 is I, right? So this is equal to G. And what is C tilde prime at 0? This is equal to LG composed with C prime, right? At 0. Which is nothing but, according to this equality, this is LG this is LG star comma I acting on X. Okay, or if you want, you can write it as LG star comma I acting on C prime of 0. Okay, good. Now by proposition 5 again, there now we are dealing with this curve C tilde of t in GLNR. So by proposition 5, there is a coordinate chart U tilde comma Rij, where again I is from 1 to all the way up to n, j is from 1 to all the way up to n. There are n squared coordinate functions. Okay, in which I am able to write C tilde prime at 0 is equal to sum over all ij's, ij running from 1 to n, C tilde dot ij at 0. Then I have del by del Rij. Okay, at G. Okay, this is should be here, and remember C tilde prime 0 is in this tangent space T C tilde of 0 GLN comma R, which is the same as T C tilde of 0 is G, T, G, G, L, N, comma, R. Good. Now, so I will need this thing later. Psi of C prime of 0, so let me write it, is equal to this matrix C dot ij at 0, ij from 1 to all the way up to n. So now I can erase everything here. Okay, good. Now I need to define a map phi from the tangent space TG GLN comma R to the space of all n times n real matrices in the following way. Phi of, so I pick up this guy because this C tilde prime at 0 is in this tangent space, and this is equal to by this is phi of ij from 1 to n C tilde dot ij 0 at 0 del by del rij at g. Okay. Now I define this guy as this matrix C tilde dot ij at 0, I j from 1 to all the way up to n. Okay, this is phi of C prime 0, right? Now I want you to see this C tilde of t. By the definition of C tilde, it's just g times C of t as matrix multiplication, right? Now I write, using components, I write C tilde ij of t is equal to sum over all k's g I k c k j of t, right? Which means I can take derivative with respect to time on both sides, and then it's the ordinary calculus derivative because we are dealing with real valued functions. C tilde dot ij at t, I can take gik out of the derivative because they are independent of time. Using the linearity of the derivative operator, we can write it as, so k runs from 1 to n, gik times c dot kj of t, right? Now I go back to the matrix notation, and the left hand side is the matrix C tilde dot ij evaluated at 0. Okay, so this is for ij from 1 to all the way up to n, and this is equal to g times the matrix Cij dot at the point 0. Here again ij runs from 1 to all the way up to n. Okay, good. Now okay, so now we have seen here that this is phi, right? So therefore phi of c tilde prime of 0 is equal to phi of, what is c tilde prime 0 is Lg star comma I of x, right? Is equal to this c tilde dot I j at 0, this matrix ij from 1 to all the way up to n. And we have shown that this matrix is equal to G times this matrix C dot ij at 0, ij from 1 to all the way up to n. And this is G times, according to this is G times psi of C prime of 0. And we know that C prime of 0 is x, right? So this is G psi of x. So what did we find finally? We found that phi of Lg star comma I acting on x is equal to G times psi of x. Okay, so psi of x is an n times n real matrix. G is in GLNR, and on the left hand side phi of Lg star comma I of x is also an n times n real matrix. So here everything is consistent and everything is a matrix. Okay, so that's what we wanted to show. We want to show that this map Lg star I as a map is a map between two tangent spaces, right? Ti of GLNR to TG GLNR. We wanted to show that this is given by left multiplication again, which is the case here. It's actually given by left multiplication by G. All right. All right. This is what I wanted to do in this third segment. In the last segment, I'll be discussing immersions, submersions, and I'll also discuss the notions of rank, critical, and regular points. Thank you for attending this third segment of the sixth lecture.